Greetings, this is Nancy Flournoy coming to you from Bellingham, Washington. I'm delighted to be able to share my work with you today. So this work is joint with Sergey Tarima, and I'm going to be talking to you about choosing interim sample sizes in group sequential designs. Most of you know that probably that group sequential designs allow studies to stop early for efficacy or futility at predetermined interim analysis times. And they are very popular because they have the high likelihood of decreasing the expected sample size while controlling type 1 error and power. I'll start with a very simple example. Let's look at two random variables, Z1 and Z2, which by themselves, if independent, would be normal 0, 1. But we have a situation where Z2 is only going to be observed if Z1 is less than 1.96. So not all possible pairs of Z1 and Z2 are observable. That's one observation. Usually when people are analyzing stochastic processes, they start with the joint probability of everything that you might observe, and they do successive conditioning on the past. But as I say, some of the possibilities in the past were not observable, so things are more complicated here. Now, instead of conditioning as in classical stochastic analyses, then we're going to condition on the experiment that was actually run. So if you look down here at the bottom, we have two estimates, two maximum likelihood estimates. And the first one, the subscript 1, indicates that you ran experiment 1. That is, you just observed Z1 and nothing else. And theta hat 2 is the MLE you would get if you ran through to conclusion. You saw Z1 and Z2. So again, conditioning is on which experiment you ran, not on all of the information in the prior stage. Now, in a study design, before you know anything, our thesis is that the stopping decision should be based, because the stopping decision is unknown, the overall distribution of theta hat, considering both stopping possibilities, should be used in planning. And when you finish the analysis, data analysis should then be performed based on which experiment you actually did run. So if Z1 is greater than 1.96, the maximum likelihood in this little example is theta hat 1. That is just the observation Z1. And if Z1 is less than or equal to 1.96, the maximum likelihood is theta hat 2, and that is the average of the two random variables. And unconditionally, the maximum likelihood estimate is a weighted sum of these two estimates according to the probability of the first observation being in the tail of the distribution, the normal distribution. So what do these MLEs look like? If you stopped at stage 1, you have a left truncated normal distribution. And if you stopped at stage 2, you have this average, which is not far from normal, but is certainly not normal. So these are important because if you do stop at stage 1 and presumably say you're stopping because of toxicity, you want to know how bad that toxicity is, and so you're measuring an effect size, and the if you assume that having stopped at stage 1, you have a normal distribution, you're going to get a really biased estimate. And in particular, you're going to think that things are a whole lot worse than they are. And you obviously think they're bad enough because you stopped. If you're planning the study, then the overall distribution is, again, not grossly different from normal, but certainly not normal. Now, I'm going to describe Pocock's group sequential design. It'll develop a little notation and we'll compare to it in a little bit. So let's consider a one-sided test with 3 stages. We have the null hypothesis that theta is equal to 0 versus the alternative that theta is equal to 1. And in the Pocock example, we have a maximum sample size, and if we're going to have 3 stages, that sample size gets divided equally into 3. Our data here are x's, and we're going to consider a cumulative sum. So we're summing all the data through the through whatever stage it is that we are evaluating. So the statistic z here with the k in parentheses indicates that we've got a standardized cumulative mean of data going through that stage. And we're going to stop the study at stage k if the observed value of that statistic is greater than a constant CP equals 1.9922. And that constant is chosen such that the probability that you will reject the null hypothesis before the end of the study is 0.05. That is, the probability you reject at stage 1 or stage 2 or stage 3 is fixed at 0.05. Now, if one takes this situation and runs it through some SAS output, in order, you have 2 conditions. You want under the null hypothesis, the rejection probability at the end of stage 3 is 0.05. And at the end of stage 3, the rejection probability at the alternative, theta equals 1, is also 0.8. And so given those conditions, one ends up with, given those conditions and the fact that you have equal sample sizes, one ends up with sample sizes in each stage of 244. So the first row here is the alpha spending function. It is increasing the cumulative probability of stopping. It goes up to 0.05, and we have the overall power. And excuse me, I've got some, these all should be theta. In group sequential designs now, what Sergey and I have done is defined a design based on ordered alternatives. And the idea behind the ordered alternatives comes from the theory of hypothesis testing with local alternatives. And there's a long literature on that subject. We have a couple papers on sample size re-estimation that talk more about this, but let me describe what's going on in this case of 3 stages. So in Tarim and Flournoy 2019, we described the theory behind this approach, and that paper is online in the archives, so you can read that if you wish. The idea is to have a constant power at each alternative rather than having the power only equal to 0.8 at the final hypothesis. So we're choosing the sample sizes to have power 0.8 all the way across the interim analyses. In order to make this feasible, we change the value of the alternative hypothesis. So at the first stage, you're going to reject if things are really terrible. That is, the alternative hypothesis is 0.3. And at the second stage, you'll reject if it's 0.2. And at the first stage, at the final stage, you'll reject if it is 0.1, that is the value that we set up the Pocock example to show. In this case, stage-specific rejection probabilities are now what we used in this paper is equal stage-specific rejection probabilities. And so we got the sample sizes for the interim analyses of 0.98, 0.98, and 576. So this looks at it a little differently. We have our constant alpha spending function for this example. And you see here that each row is various alternative hypotheses. The first row is the null. So the first row gives the alpha spending function cumulatively. The second one is 0.1. So that is the hypothesis where that corresponds to the way we set up the Pocock. That is the probability of rejecting at the end of the third stage is 0.8, but we will reject at the end of the second stage with probability 0.8 if under the alternative that theta is 0.2, and we will reject at the end of the first stage with probability 0.8 if under the hypothesis that the alternative is 0.3. So to compare with Pocock, we have to change the alpha spending function from the example that's in the archive. And so we look at our approach with the Pocock alpha spending function, and we find that we get 80% power at each stage and smaller sample sizes. So here is sort of a summary picture of what's going on with the power here. We have our ordered alternative hypotheses approach on the left and Pocock's approach on the right. And if you look first at the dashed line, this is the power function for stage 3 under both approaches. And they have in common that at theta equals 0.1, they give you 80% power. And so where they differ then is under the other stages, we get 80% power for these alternative hypotheses, whereas under the standard approach to group sequential design, the power is way above 80%. So you might say, well, that sounds good. I mean, you get more power doing it the other way. What's the problem? And the problem, of course, is that you pay for that extra power by having more subjects. So there are lots of questions left to answer with these designs, but we think they're very intriguing and encourage people to look at them. So our conclusions are the possibility of early stopping changes the distribution of the MLEs. It becomes non-normal. And we have presented to you a new design which controls overall type 1 error while also controlling statistical power at multiple alternatives. Thank you.